Alright, what I want to do here is have a look at current. Current's quite simple. Hopefully you've watched the first 4 minutes of the other video, which was on voltage. Voltage is a bit trickier and so is resistance. But current, it's not too bad. You all know now that current is equal to charge divided by time. And the charge is coulombs, time is seconds. And that 1 coulomb is equal to 6.25 times 10 to the 18 electrons. So what that's basically saying is that when you've got a wire and you've got little electrons coming past that point, after 1 second, if you've got your stopwatch and you're counting them, if 6.25 times 10 to the 18 electrons have gone past, then you've had 1 amp. You've got 1 amp. So we don't use electrons obviously because that's 6 million electrons, which is a lot. So electrons are small, but there's a lot of them in a small space, more than you would think. So we would call that that many per second will be equal to 1 amp. Now that's the electron flow, so that means this must be negative over here and this must be positive. But we've said that current goes from positive to negative. So the electron flow is opposite. So conventional current treats it all as if it's positive charges, which it's not. But it all works out because the numbers are exactly the same, right? So if we ever want to know which way the electrons go, we just know they go the opposite way. Okay, not much more to current really, but what we'll do is a little interesting physicsy thing right now, where we look at the actual speed of the electrons. Can we work it out? So if we've got a wire, and it's cross-sectional like that, and we say between these 2 points, this would actually be the distance the electrons have flowed. All the electrons in that area have flowed that far in that time. So this is delta x, and this is area. So the volume of that little element there is equal to A delta x. Now if I have a number, I'll call it n, and it's the number of charges per volume, then if I times that by the volume, then I've got the total Q. So the total charge in that little area there is equal to n A delta x, right? N A delta x. Now delta x is equal to, or distance is equal to velocity times time. So we can actually call that v, velocity, times time. That's the total charge in there, all right? So we come back to our definition of current, which is total charge that passes a point, and total time is your current, right? Per second that comes out. Now, we've just said that that total charge is equal to n A delta x. No, we already got rid of the delta x, didn't we? Because we said, so n A v delta t times charge. Oh, I didn't even put that on there, did I? I had to actually put on that charge, because you have to multiply the number of charges times the charge for a single charge to get the total charge. So we're good though. N A v delta t times the charge. But we need to divide that by delta t, which we can, and then it cancels. And so we end up with I being equal to n, number of charges per volume, A, times the velocity, times the charge. So if I want the velocity, I can just rearrange that, can't I? Velocity will equal I divided by n A q. Now if I go to the trouble of doing that, what's that velocity of? It's the velocity of the electrons. Because basically we've said if they move a certain distance in a certain time, that's their velocity. So if we divide it by the current, by the number of charges per volume, times the area, times the charge on a single charge, we'll work it out. And if you put the numbers in, because n, the number of charges per volume, this is the number, and I sometimes get my classes to work this out, it's a really big number, it's 8.5, that's not a big number, times 10 to the 28, that's a huge number of charges per cubic meter. Now cubic meter is big, right? There's 1 billion cubic millimeters. Isn't that hard to believe? 1,000 times 1,000 times 1,000. There's 1 billion cubic millimeters in a cubic meter. So we can take that down by 9 immediately for a cubic millimetre. But we've still got 10 to the 19 charges in a cubic millimetre of copper. So when we actually work this out, although a coulomb is a huge amount of charges to pass a point in a second, there's a huge amount of, and you can see there's almost 10 times more electrons than that in a cubic millimetre. So they actually move very slowly. If we work it out, it comes out at about 1/4 to 1/2 a millimetre per second. So the actual electrons move very slowly, right? That's how fast they move. Anyway, that's current.